Okay, we are with the alkene today. So on this we have reactions that's showing a variety of functional groups get converted to alkene. Again, before we jump on the actual reaction, if you have to monitor the reaction, there you can easily see the double bond is forming. That's the difference by elimination. So double bond will be easily detected by UV, and the IR itself will give you a medium to the weak signal for it. And there you have a sp2ch relatively easy to detect. So from here to there, not easy with the IR or UV, though there is a little difference. NMR will be also useful. So nothing over 4.0 here, not even 2.0 ppm, but you already have sp2 carbon holding hydrogen, and that's appearing over 4 ppm. And telling these apart is not easy, but number of hydrogens in the alkene region of the NMR, you have only one, but there are 3 and the 2. Also, the splitting pattern will tell you the difference. Mass spec also not easy. For alkyne, the IR is also useful for the triple bond itself, and also SPCH bond is different from CH2 sp2ch bond, the stretching mode. Even if you want the hydrogens on this side and that side, you can tell apart by looking at the nosy two-dimensional NMR through the space. You can have some cross peaks, or you have a different coupling constant between this hydrogen and this hydrogen over here versus this hydrogen with this hydrogen there. And so you can distinguish every single alkene hydrogens. This one's easy again with the OH and IR, and mass spec is especially useful for chlorine. So we are ready to monitor the reaction. So let's get to the synthesis. These are the reactions we have done before. So simple elimination, but there's no leaving group. So you have to first put leaving group on the tertiary. So you want to be selective, then you do elimination, but you want the ZF, so try to control the size so you get the ZF product. If you want to be more cautious, maybe you can substitute the bromine after first step with the OH in the SN1 maybe. If you do SN1 with the hydrox water, upon heating you get hydroxy group replacing Br. Then you do sulfuric acid with heat, then you might have a better result getting this more substituted alkene. All of them can rearrange to the tertiary carbocation, so you can imagine that you can do elimination there using rearrangement feature in the addition reaction. So I did this kind of similar reaction before, but you can add HCl, then addition reaction, we'll put hydrogen here, here, and then carbocation on the tertiary, this time secondary, but hydride shift to the tertiary. So you will form common carbocation there. Then the chloride will give you this compound. Then you can do elimination. Same manner that we did before, considering steric issue. But also it is likely if you put just the sulfuric acid and heat up, the hydrogen go on and create the tertiary. Then due to the sulfate under heating, it will attack beta hydrogens and create Zaitsev product in one step. I went over this before, but let me try slightly different route this time. What if you do H3O plus? Hydrogen goes to the terminal, and you got the carbocation. Water goes there, so you get the sp2 carbon holding water with a double bond. Then water comes and take this away. And you get the OH. There you have an enol. Enol is not as stable as a keto form, so you have an enol keto tautomerization happening. Sorry. So the tautomer of this is forming when H plus, because it's under acidic, sorry, because it is under acidic condition when you put H plus. And the double bond is able to pick up hydrogen. And it's a better drawing arrow now, but let me show you stepwise just to explain better for you. So hydrogen goes there, CH2 turn into CH3, and the positive will form there. However, then there is a resonance like I should be doing here. So you form double bond here without the plus sign there, but here. Okay, so then water comes and take this away, and you have a keto form. Then what you do is you can reduce this. So first you add I'm doing here, right? So H3O plus, and then number 2, you reduce it using, say, sodium borohydride. The partial negative hydrogen attacks on the carbon and breaks off. So borohydride attacks, breaks. Then you can create this. Then you quench with a H plus. And you got this. Then you do simple H2SO4 heat. You can get double bond here. If you want double bond there, then from there you can continue. Instead of OH, you want halogen leaving group, so you put SOCl2 instead of HCl, because HCl is going to replace this, but not on this carbon, right? Water forms by hydrogen of hydrogen chloride, and then water leaves, then positive charge shift, so you don't get the double bond here. You will get it here or there, depends on your size of the base. So you replace the chlorine, you replace the oxygen with the OH with the chlorine, then you do Hoffman elimination to get there. So what you need is first same steps, but instead of this you do, let me put it there, you do sodium borohydride. Third step, what did we do? We did the thionyl chloride. Then step 4, let me put it here, step 4, we use the big base like isopropyl oxide to get the Hoffman elimination, so you can get there. And there are many other ways, but I wanted to show this route this time. Alright, so the remaining ones are straightforward. This one we did mention a couple of times. You can just do simple dehydration with the sulfuric acid. Then E2, but be careful with the size. So we use a small one. And you get the size of product as a major. So these are some of the methods you can create alkene. Now let's move to the reactions with the alkene to form other functional groups. So basically you are connecting this chart with this chart. So you go from here to there to there. And you can even connect more afterwards. I think I showed you enough before. Here we have some of the reactions with the alkene, and there are 3 different isomers I showed you, but I'm gonna work with these 2 for certain compounds on the right. So any alkene can go to alkane using 1 mole of hydrogen gas with some sort of catalyst. And you move from one type of alkene to the other types of alkenes, vice versa. You should try, but then again, in order to get there, you know, you need Hoffman elimination, so you have to add your leaving group. So in order to form this double bond, your leaving group has to be on this carbon, meaning to this alkene, you need to add something in anti-Markovnikov fashion. So I would choose halogen using HBr and the peroxide rather than OH using borohydride, because to remove OH, you have only 2 options. You can do sulfuric acid, then you get most likely more Zaitsev product. So then you want the halogen. In the halogen substitution, if you were to go to halogen again, why would you put the OH in the first time, right? So it's better to go for HBr addition and anti-Mark. To get there, then you do E2 Hoffman with a big size of base and strong one, not E1, because then E1 will lead to the rearrangement to the carbocation on the tertiary, so you wouldn't be able to get there. To get this, yes, you want regular Markovnikov addition. Let me try halogen again. So you get HBr. Then out of this, you get the intermediate, not intermediate, the precursor, something like this. Then you use a big, really big base, so to abstract this beta hydrogen for your E2 reaction. And don't forget, even when you're working with the long step synthesis, they can throw in some of the structures that you have to always check the arrangement of the hydrogen and the leaving group as a syn or anti on the same plane. So the big base you want is, again, for the tertiary, it doesn't have to be so big. Even ethyl group will do it, but we want to be sure. So let's go for isopropoxide as a base. Then you get E2 right there. How do you get triple bond there when you have a double bond here? Meaning you need to have 2 halogens there. If you go to a previous video, I gave you a homework to exercise there. So how do you put two bromines here? Before talking about putting two bromines or leaving groups here, which is not easy right now, as you can see, normally converting double bond, double bond, say anti-transform to the triple bond, you do anti-addition of bromine. It's a step number one. Then from there you get, I'm gonna ignore the stereochemistry for now, you add Br like this. Then you have two leaving groups, so you can do two equivalents of a strong bulky base, or even amide would do it, or two equivalent of hydroxide. They do it with a very high temperature, like 160 degree, because each one of them find the beta hydrogen and attack here and form one double bond, one pi bond in the double bond. Then you'll get to this point. Then you have your anti-hydrogen on the beta carbon, second mole of the base under heating comes this way, and you do E2 and you get to the triplet. But you cannot take that strategy here, because if you put bromine here and there, you don't have a beta hydrogen here to remove bromine going there, so you cannot form triple bond here. But we don't want triple bond even there, right? You want triple bond over here, so we want two bromines, but you have already 1, 2, 3 things, so you cannot add two bromine. So what you do is, instead of putting two bromines here, which is impossible unless you remove the hydrogen, you can think of the ways of doing it, but I would go easier way. If you make this one, we talked about it before, then you can add Br2, so Br2, right? And then you can do elimination twice, so 2 equivalent of OH minus with a lot of heat, then you can get there. So you know, converting this alkene to that needed anti-Markovnikov addition of Br here, and then E2 Hoffman elimination there, right? So we want HBr with the peroxide with little bit of heat. Then you put bromine here with no double bond. Then you do E2 with a somewhat bulky base, isopropoxide, to convert that. In the third step, Br2, and the fourth step, 2 times of elimination. You get there from here. Okay, next entry is which one? I just had 2 arrows. From there to these are easy, because you do just a regular Markovnikov addition, so H3O plus, anti-Mark addition, you know, borohydride, and taking off the boron. Then you can get there for anti-Mark. Sorry, I think I messed up. So this thing for this, and this condition to make this one from this alkene. Things get tougher to make these, but you know, when you get this double bond and this double bond, then you can think of the methods, right? So you need to know how to get there, and we talked about it before. However, making this even from this is not as easy. If you try to do Markovnikov addition, because it's the primary and the secondary, after putting to get there, after putting H plus, step 1, H plus there, you get the carbocation on the secondary. However, the carbocation on the secondary is not stable enough, so shift to the tertiary, then you don't get this. So you have to think about the putting OH or any oxygen nucleophilic compound like alcohol or acetate and all kinds without rearrangement. So we don't even use the H plus in that strategy. Hopefully you remember that. But to get there, okay, from here to there, you can use the one without rearrangement. If you think about the two general mechanisms of addition, there is a traditional one that allows the rearrangement, but there is a non-traditional bridge the mechanism. So for that, you are using somewhat bigger atoms such as mercury with the conjugate base and 2 plus sign on mercury. Then the base is a weak base normally, so to put OH, you can use OH with the extra hydrogen. If you are putting something else here, then oxygen with something else, and then the hydrogen to make it weak base. So that should give you OH on the more substituted secondary carbon from this alkene. If you try mercury here, the OH goes on the more substituted tertiary, right? Then in order to remove the mercury, you reduce it using sodium borohydride. Then you can get there. Getting this is easier. You do anti-mark addition on this one. If you're starting from there again, you have to come to this first. Then you try anti-mark addition of OH using these conditions to get there. So you should be very versatile, going from something to something else with a little change. Just shift of the double bond or putting same functional group wherever you want. So that's the minimum toolbox you want to have when you actually jump into the multi-step synthesis in total synthesis. Okay, so one of the last reactions I want to touch is there are many ways of putting different number of halogens, but this is easy with the Br2 there. And if someone asks again, you can make this from that, then you have to first go to this from here to there, then you add X2 to form anti-addition of 2 halogens. To make this from here, it's easy. You do MCPBA from there. MCPBA from this compound. But from anything else, you have to go back to the more stable form of alkene to do it. Then out of this, you can make alcohols, yes. You can make diols using osmium tetraoxide or KMnO4 at low temperature. But you can also create a ketone aldehyde carboxylic acids, these things, using ozone and also KMnO4 under heating. But then you are losing some carbon numbers here because those conditions will cut the double bond. So if you think of the bigger, longer step, coming from alkane, how to make a ketone with a different number of carbon with a CO double bond in different places. Then you have to create double bond in different places to put, carbonyl group here or there. So you have these controls. Control of the regio isomerism first, then you can conduct the oxidation reactions. Depends on how much oxidation you want. Do you want aldehyde or carboxylic acid? you also need to choose. For aldehyde, you choose little weaker one, like ozone in the first. In the second step, you put some reducing reagent like a sulfur compound or zinc with the mercury amalgam. For carboxylic acid, you further oxidize aldehydes. You don't throw in reducing reagent. You just treat them with the ozone or KMnO4 and heat them up. In addition, if you have the triple bond here, but you like to put something over there, then retrosynthetically you want to cut there and create two syntons, and you have this synton over here already, and the hydrogen sitting on the sp carbon is quite acidic because the conjugate base of it, the carbon negative of sp, is somewhat stable. So out of these two carbon, you will prefer to put negative charge on the sp rather than sp3. So the syntons you come out is this with a negative sign. Then you can obviously put lithium and sodium or any other metals, magnesium, copper, whatever. And each electronegativity of the metal will determine how much negative charge is in the ionic form that controls the reactivity. The more ionic it is, the more reactive, the more dangerous it is. So if you want to be somewhat less reactive, you want to have the metal that's more electronegative, like magnesium or copper, even palladium. Depends. So the other carbon, you have to have a leaving group to put on like plus charge. Then you can attack here and you do SN2. Then the problem is, how do you make this precursor to do this last step out of this? You have to get rid of the hydrogen to form unstable carbanion. So the principle was always the reactant base has to be more reactive than the product base, conjugate base. So you use something like a butyl sp3 carbon negative with a lithium, extremely ionic counter ion. Then you can obviously use sp3 carbon with a big ionic character to take away the hydrogen, and you create this. Then you can do this reaction to complete. You may have some of the elimination reaction due to the size. This is a secondary, but you cannot avoid it at the moment. If you learn more organic chemistry, you can choose type of leaving groups and solvent to promote more E2, more SN2 rather than E2. But for sophomore organic chemistry, you don't have to worry about those details. And another interesting functional group, the epoxide, it is used to make a polymer by opening the epoxide ring. It's under ring strain, so it's easy to open up, but the oxygen is a poor leaving group, so you either use Lewis acid to make the oxygen better leaving group like H+, or you use an extremely strong base to create oxygen negative base as a conjugate base. So you can do in two ways. You can put H+ and then create better leaving group. As soon as you form oxygen positive, this is a positive sign, then you are weakening this bond with a more substituted carbon that bears a positive charge better. So it's easy to attack here. But this time, under the acidic condition, your base has to be weak base. So if you are using, for example, water as a base or alcohol as a base, this will go to tertiary carbon. Depends on temperature, it will open up already, and then the reaction will be in racemization if it's possible. So you get OH going down this way, and the water come up here, and then one of the hydrogens will be taken away by the water. So you get anti-addition of diol, or if the base wasn't water but alcohol, you get ether here and then OH there. But if you are using strong base in basic condition, not acidic condition, this will right away attack. But if you know, you attack the carbon, which is SN2 fashion, so you get better chance to do SN2 on the less substituted secondary with a low activation energy than tertiary with a steric hindrance that causing the high activation energy. So it goes here and open up this way. Therefore, oxygen come down here, OH goes up there, pushes down the methyl group and hydrogen, and you have now quenching process. You add some source of H+, you get the diol or other functional group, depends on what base you are using. So you can open up this way. So you can keep going, and this way you become more natural in total synthesis. So I'll have to wrap up here. So we looked at the alkane going to the alkyl halide, making double bond and alcohol, and then you can go back. So those are the core of the functional groups interchanging. So what we have left is dealing with alcohol. Then after that, more oxidized the form of oxygen compound, so ketone, aldehyde, carboxylic acid, it's coming up. So I'll see you next time.